Hello, my name is Roland Balint. I'm originally from Germany and now I'm a PhD student at Åbo Akademi University. And my research is focused on aging of recovery boiler deposits, and this means that I study the changes within superheated deposits that take place over time. So in this pie chart, the global energy supply by source for the year 2018 is shown. As you can see, fossil fuels are still dominating with a share larger than 75%. But when comparing this to the Finnish energy supply by source, the share of energy being produced from renewable resources is significantly larger than the world's average. The biggest source of renewable energy in Finland originates from biofuels and waste. A more detailed breakup of the separate renewable energy sources utilized in Finland highlights the key role of the forest industry. More than 75% of Finland's landmass is covered by forest. Thus, the forest industry is an important factor in the country's economy and also its biggest energy supplier. The focus of my presentation will be on black liquor, the largest renewable energy source in Finland. Black liquor is a byproduct of the kraft pulping process, where fiber is extracted from wood by the use of a chemical solution consisting of sodium hydroxide and sodium sulfide. The liquid solution of the spent chemicals is called black liquor. The flowchart shown on the bottom right presents a summary of the single steps within the kraft pulping process. The overall process is a closed loop, meaning that the used chemicals can be recycled and reused multiple times, increasing the sustainability of the overall process. In the past, the pulp and paper industry had a rather poor image among the general public. Pulp mills were associated with bad odors, and also the effluents were assumed to be polluting the surrounding waters. As shown in this excerpt from a newspaper from 1907, when people were asked for their opinion on the pulp mill that was about to be opened close by Kemi. But over the last decades, a lot of research has been carried out to further improve the overall pulping process. The graph shown here presents the annual number of publications on black liquor combustion, and as you can see, it has increased constantly over the last decades. When looking at the breakdown of which countries contributed the most to these publications, Finland has a leading role in the field, as it takes the first place with the most publications. The impact of this ongoing research can be seen when looking at the total annual air emissions caused by the pulp and paper industry. Despite an increase in the overall production of pulp and paper in Finland since 1992, emissions from pulp mills could be reduced significantly, with CO2 being reduced by half and sulfur and particulate emissions being reduced by almost more than 80%. The focus of my research project is connected to combustion of black liquor. As a fuel, black liquor has rather unique properties. It contains spent pulping chemicals, thus the sodium and sulfur content is very high. Besides, up to 50% of black liquor consists of dissolved raw wood. The key interest when burning black liquor is the recovery of the spent pulping chemicals. Therefore, the combustion unit is called recovery boiler. It can be easily identified in the image of the pulp mill as the largest building. During combustion, the pulping chemicals form a smelt bed at the bottom of the boiler, which can be extracted and further processed to be reused in the pulping process. Hot flue gases that are released during combustion are utilized to produce heat and power in the upper region of the boiler using heat exchangers. Together with the combustion gases, ash particles and vapors of inorganic compounds are transported to the heat exchangers where they cause deposit formation. Here in this picture you can see clean heat exchanger tubes. But over time, ash particles deposit on these tubes where they can cause severe operational problems within the boiler. The formation mechanisms of such deposits were studied extensively over the last decades. The main compounds of deposits in recovery boilers are sodium sulfate, sodium carbonate, sodium chloride, and the potassium counterparts. A more detailed analysis of such deposits showed local changes within deposits over time. These changes cause enrichment of corrosive alkali chlorides towards the steel, thus increasing the risk for deposit-induced corrosion. The goal of my research is to better understand these processes that cause changes within deposits over time. The experimental approach to study these mechanisms can be divided into three parts. Deposits are obtained directly from the heat exchanger surfaces of recovery boilers, which are provided by the boiler operators. In addition, measurements were carried out in the Finnish recovery boiler, where deposits are collected on an air-cooled probe. And lastly, laboratory experiments using synthetic ash deposits are carried out to study the observed mechanisms under well-controlled laboratory conditions. All these experiments are intended to complement each other, making it possible to not only observe the changes within deposits over time, but also being able to explain the underlying mechanisms. The image you can see here has been produced by an electron microscope. It shows the cross-section of a synthetic laboratory test sample before exposure to our experiment. The synthetic deposit consists of distinct single particles of uniform chemical composition. During the experiment, the deposit is exposed to a temperature gradient. This temperature gradient builds up due to the temperature difference between the colder steel and the hotter furnace air. And it has been identified to be a key role when it comes to these changes within the deposit over time. The image on the right, you can now see that the synthetic deposit has changed after it has been exposed to this temperature gradient. Several mechanisms are responsible for changes within this deposit that alter the morphology and chemistry within a deposit over time. Enrichment of corrosive elements in the molten phase can result in local changes of the deposit's melting behavior, and this melt can also move towards the steel. Furthermore, gas phase transport of alkali chloride towards the steel could be identified. All these mechanisms increase the risk for deposit-induced corrosion, and in addition, melting and subsequent solidification of the deposit can impede deposit removal. The goal of my research project is to provide new insights into these mechanisms that take place over time after the initial deposit formation took place. A better understanding of these mechanisms can help to better control deposit-induced problems such as corrosion and deposit removal on heat exchanger surfaces of combustion units which are used for heat and power production. So to summarize this presentation, the importance of the pulp and paper industry as Finland's largest renewable energy source has been highlighted. Finland has a leading role in the recovery boiler technology, also due to the extensive research that is carried out throughout the whole country. Ash deposits on heat exchangers are still challenging, especially when trying to understand the changes that take place within deposits over time. And those changes could be identified to be very strongly dependent on the temperature gradient they are exposed to. And the results of my research aim to help to better understand these time-dependent changes. And the overall goal is to be able to better predict and control deposit-induced problems. Thank you.
Okay, thank you, Roland, for very nice and interesting presentation. I worked with the same topic myself around black liquor and recovery boilers myself during my doctoral studies, so this was a really nice reminder on this field, so this was nice on that sense as well. If we think about your work and if you really hit the bullseye, like with your work and results, what would we have there as a result of this?
Yeah, we hope that we can basically prevent corrosion with my research, or at least be able to very precisely predict what leads to the corrosion and how can we maybe also work around those mechanisms or avoid that, for example, the molten phase reaches the steel surface, as we could figure out that the local melting temperature can change, and therefore you can have corrosion taking place in places where you would not expect it. But those new mechanisms showed that there is other factors that have to be considered when thinking about corrosion, and yeah.
So there's the stakes are huge.
Yeah, and we also hope that it's not only relevant for recovery boilers, but then also being able to extrapolate it to all other kind of biomass boilers that we will hopefully see in the future.
For example, waste combustion is something that we will always have, so I think your results could be also applied to that
actually
field.
A colleague of mine carried out experiments with deposits that simulated rather deposits that form in waste combustion than in recovery boilers.
Okay.
The problem is just that it gets more difficult as much more elements are involved there. So recovery boilers are the starting point, as the deposits are very well defined and rather simple compared to other resources.
Excellent. Okay, all the best in the future. Good luck with your work and thanks for being part of this
Thank you.
production. Thank you.